Hello, everyone. Thank you for tuning in. My name is Statistical, and I would like today to sort of review a bit some of the statistical models we use in genetics, starting from the simplest of all, the linear model with a single predictor, and then complexifying them until we reach the complexity of the models we use in genetics. I'll start with a short introduction of the data sets or that I'll be using as a toy example. It's the iris flower dataset, and it contains 150 observations of different flowers, different irises, for which we have sepal and petal length and width, and then we have the species collected. So let's start with the simplest model of all, a simple linear model with a single predictor X. So Y is our variable of interest. Let's assume BMI for the sake of the example. X is age, for example, again. And then B is the association we're interested in between X and between age and BMI. We can estimate it using maximum likelihood estimation, and then the model looks like this at the bottom. I like this vector representation or matrix representation because they actually look like the data set we have in terms of the columns of the BMI column and the age column. So I find that quite useful. I hope you too. We know from the linear model theory that the beta is a function of the covariance between X and Y divided by the variance of X. We also know the formula for the correlation coefficient R, which is also a function of the covariance between X and Y. From these two formulae, we can easily derive the relationship between the correlation coefficient and the linear regression coefficient B. And as you can see, R is a function of B, which is scaled by the standard deviation of X and Y. From this formula, it's very apparent and obvious that if the variables are standardized, X and Y, so the variance equals 1, the standard deviation equals 1, then the correlation coefficient is the beta estimate coefficient. Well, let's check this very quickly. So we fit this model on the iris dataset. So sepal length as a function of petal length. And then we have an estimate of effect size with a standard error and a p-value. We can check what I've said before about this equivalence between beta and the correlation coefficient. So here we estimate the correlation between the two variables, which is estimated to be 0.87. We can do the same in a linear model framework where we scale, so standardize the variables, and we end up now with a linear estimation or a linear model estimate, which is the same, 0.87. So good to see that the practice fits, aligns with the theory. All right, let's complexify the model and to go to multiple regression. So let's assume we're still interested in our Y variable, let's say BMI, but now we have several X variables which we want to fit in the model, such as age and sex. So in this Y equal XB plus E, B is now also a vector. So it's beta B1, B2, which are the marginal association of each of the X variables. So our model now looks like this. X becomes a matrix of the different columns, and then B is a vector of different values. So this can allow to define what's called partial correlations or multiple correlations. But more interestingly, this is this global measure of fit called Rsquare, which I'll come back to in a moment, but is important because it can summarize the association between Y and several X variables. Okay, let's have a look to this. So here we fit a model with several covariates. Some are continuous, such as petal length and petal width, and then species is discrete. So we have one estimate per species compared to a reference value, a reference class. So here we have several estimates and then a multiple R-square for the model. All right, so we can further generalize this model into what's called generalized linear models. So this means that now Y, our variable of interest, doesn't have to be normally distributed. It can be a disease status, so a 0-1 variable. It can be a number of symptoms, so a count, or follow other type of distributions. So here in the example, I've put SCZ, which is the schizophrenia case control status if you have it, but it can be anything that's normal or not. The estimation of the parameters still relies on maximum likelihood, and here are all the distributions we can fit. So Gaussian, binomial, Poisson gamma, inverse Gaussian, for example. So let's do this quickly. So we take our sepal length variable, and then we discretize it, assuming that above 6.5 centimeters, the sepal length is considered long, or it's considered long. So here is our logistic model, because we fit a discrete variable as our outcome variable, and still with the same predictor as before. So we use the GLM function in R, and then we specify the link function or the family here as binomial. So as before, we still have an estimate. So here in the case of a logistic model, exponential beta is the odd ratio. But we can also get some of the other metrics of interest. Okay, let's talk a bit more about R-squared and the variance explained. So coming back to the simplest model of all. So X is a single variable, and we only estimated one parameter B in the model. We can write the variance of this equation. So the variance of Y is actually beta squared, the variance of X plus the variance of E. And we can easily see from this that the variance explained by the model is the variance of beta squared variance of X. So the variance explained by the model, R squared, is this divided by the variance of Y. Here we actually recognize the square of the correlation coefficients, which we derived in the second slide. This is also known as the coefficient of determination of the model. Mind you, we can still derive measures of variance explained, or R squared, in the context of multiple regression, where we have several predictors x1, x2. Here, it becomes often simpler to use the variance of E, which is easier to estimate than the variance plus the covariance of the different terms. So in summary, the R-square allows to measure the association of a single variable, but also combined association of several variables. For logistic and Poisson regression, we use pseudo R-squares, which can be, well, there's a choice of them, but more or less they're always derived from the log likelihood, or the likelihood of the model. And so R-square is a measure between 0 and 1, expressed, scaled in terms of the proportion of variance of Y. Okay, let's have a look to what I said before, which is that in some simple case, R-square is the square of the correlation. So here we take our simplest model too, with a single predictor. The variables are squared, so the estimate of our model, linear model, is the correlation coefficient. And if we take the square of this, we actually find the multiple R-squared, which was calculated by the model. So once again, the practice fits with the theory, which is always nice. Okay, now with a multiple regression model, so we fit several variables in our linear model. And if we want the global R-square, well, it's already calculated by the model, but if we want to double check it, we take 1 minus the variance explained by the residuals, and then we find this multiple R-square. Okay. All right, let's try to be more ambitious now and fit a multiple regression with many, many more SNPs. So let's assume you get given a matrix of observed SNPs. Let's assume it's the UK Biobank. So you have 450,000 individuals of European ancestry, but you have around 16 million usable SNPs. So your model Y equal XB plus E becomes this huge model, where you fit your whole matrix of SNPs all you want to, and then the beta or the B vector is extremely long. Well, if we try to do that in R using the standard approach, well, this fails. And that's because this model is not identifiable. We don't have enough degrees of freedom to estimate all the parameters. Basically, the rule to remember is that we can estimate n-1 parameters in a linear model. And here we have 16 million SNPs, but we don't have 16 million individuals. So how do we handle this? How do we tackle this challenge? Well, we can actually fit this using a random effect model. So we still fit the model, y equal xb plus e, but now we add a constraint to b, so the model becomes identifiable. And the constraint is typically b is normally distributed with mean 0, and then a scaling factor for the variance of b, which is SG squared divided by m. Again, we can write the variance of y, which is the sum of all the beta x variances, which is well, SG squared again. So X here is the full matrix of SNPs, standardized. We'll come back to this. And so B here can be seen as the marginal SNP association coefficient. So it's the association of each SNP with a variable of interest Y, but conditioning on all the other SNPs that we have observed and fitted in the model. As I said before, this model is now identifiable, but has an added constraint or hypothesis on B, which is it's normally distributed and unimodal. But what's convenient with this formulation is that R-square, the R-square of the model or of the random effect, only requires estimating SG square and the variance of Y. I said that we can fit those random effects on highly dimensional data, but we can also fit it on sort of low, on a lower dimension. So just to compare the two, here's a linear model, simple, where we fit species as a factor, as a discrete variable. So we end up with two estimates of effect sizes of these two species compared to the reference species. And we end up with a multiple R-square of 0.62. Now we can fit, using the LMER function in the LME4 package, we can fit species also as a random effect. So we don't find species anymore in the fixed effects section, but we do find it in the random effects group, where we can calculate also the proportion of variance, which is here 0.70. So it's slightly different than what we get, but mind you, and we're trying to approximate or estimate a normal distribution from 3 values, which is not necessarily going to be very easy. And also, as you can see here, these three species differ quite widely in terms of sepal length and then the distribution around the mean. All right, so now we have a model where we can fit large effect or large size data, but we can reformulate this under a simpler, arguably simpler form, which is y equal g plus e. So now g is a single vector for individuals, as you can see at the bottom. So we have a single g value for individual, meaning that it's the genetic breeding value of that individual. It's a single value which corresponds to the genetic value for this trait y for this individual. But we have now, so G is still a random effect, normally distributed, centered in 0, but its variance covariance structure is more complex, as defined by this matrix GRM here. And that's to account for the fact that since we only have a single value per individual, well, the G values are somewhat correlated throughout our sample. It could be due to familial or cryptic relatedness, or other things. But so that's what this GRM sort of models or takes into. We have a formula for the GRM, which is actually derived from this X matrix, which we had in the previous formulation. And as the two formulations are equivalent, we still have the same value, the same formula for the variance of Y. If you're wondering what these G values sort of look like, we can visualize them in the model we estimate. And they sort of this somewhat normal distribution, with some individuals having larger values, meaning that they have a higher genetic breeding value, and some have a lower value. Mind you, this model may start to ring a bell from what you've seen in the previous days. All right, just to emphasize that these two formulas are one model and one are equivalent. I've just written them down here. On the left-hand side, I guess the formula emphasizes more this X full matrix of SNPs. So there's the focus is on these high dimensional data that we're trying to fit. On the right-hand side, the emphasis is more on this latent factor G, which is not necessarily observed, but of which we know this GRM, so the variance-covariance structure. All right, so we've seen models with fixed effects, simple effects. We've seen models with random effects. Well, now here's the best of both worlds. Linear mixed models where we can fit fixed and random effects in the same model. So we have covariates Z, such as age, sex, and genetic species, for example, and then we can still fit our full matrix of SNPs here under a random effect. All right, so now that we have these models, let's focus a bit on some of the objects, and starting by the GRM. So the statistics tells us that the GRM is X times its transpose divided by the number of SNPs M, X being a matrix of standardized SNPs. So how do we go from the raw SNP matrix to the standardized matrix? So here's the SNP matrix. So each SNP in bold corresponds to a vector, so a column. So the standardized one is simply each SNP divided by its mean, where we subtract the mean and divide by the standard deviation. Well, remember that for SNPs, the mean of the SNPs is a function, is 2p, so p being the frequency of the reference allele, and then the standard deviation is the square root of the variance, so 2pq, the square root of that. So this means that we can replace this in the formula and get our formula for the matrix of X, our standardized SNPs. All right, X times its transpose. So we've got X at the bottom here, where each individual corresponds to a row. The transpose of X means that now each individual corresponds to a column. So we will calculate each element of the GRM. Let's assume the first one here, where it's simply the sum of the cross products of the pairwise elements of the X matrix. Same thing for this off-diagonal element. So we're going to calculate the products of each X1 values, X2 values, and then sum them across the genome to get this, which is in practice a covariance of the two individuals in terms of their genome or observed genome. Okay, how does that really relate to the formulas you've seen before and you're going to see tomorrow? Well, so 1 divided by m times the sum of the cross products. So xmy times xmj, sum of m. Well, that's the sum that we recognize here by plugging the values, the formulas we had before, and we actually recognize the value, the definition that was given to you as the GRM elements. All right, so you might be thinking, well, we haven't talked about statistical power yet. Well, here it is. Just a quick recap. So statistical power is the probability of detecting a true association. It's a function of the type of effect, fixed or random, the hypothesized effect size, the sample size, and the risk alpha, which is often fixed and assumed to be 5%. So I'm relying on this paper by Peter Vischer and colleagues, where they derived the statistical power formulas for variance components and for genetic correlation coefficients. What they end up basically with this formula, which is that the variance of the estimate, from which we can easily access the power, is a simple function of n, the sample size, and the variance of the GRM, so the variance of the off-diagonal elements of the GRM, which is approximately 2⁻⁵ in human populations. So we can get a very simple estimate of power simply based on the number of sample sizes. So yeah, the bottom line and the take-home message is that power depends on the variance of the GRM of diagonal elements. And you can use those shiny links to calculate power yourself. All right, a quick point about association testing. So all these models actually belong to a common framework. And then the central concepts behind those frameworks is this likelihood, which was mentioned to you, I think, in the first few days. So the idea for association testing is to use nested models, where we're going to compare two models, one being the subset of the other in terms of variables included and not in terms of individuals. So here's an example. We've got this full model, which is a linear mixed model with fixed and random effects. And then we drop the random effect G, and we end up with nested model, which we can compare to the full one. The test statistics is a function of the log likelihood, so which is this L theta, and that follows a chi-square distribution of parameter Z, Z being the difference of parameters between full and nested model. Just a side note, the random effect, even if it models a highly complex matrix of SNPs, the dimension is still 1 because it's scaled by this the variance of the random effect, which is the only thing we need to really estimate. Okay, so here's a quick summary. So I hope I've convinced you that you can see linear mixed models as an extension of GLM. So there are extensions in the case of highly complex and high dimensional data, not necessarily complex data, but on which you want to fit a normal distribution of effect sizes across a certain set of predictors. But there can also be extension in the case where we don't have observed necessarily measurements, but we have a known structure of variance covariance for the random effect. Another important, I think, point from this presentation is that R-square is a useful measure of association, which can capture the association of a single variable, but also the association of several variables. As we've seen, the GRM, which is the same as which you've seen before in other presentations, is the variance covariance matrix of the random effect, and it's sufficient to describe the random effect, meaning that we don't necessarily always need to observe the X matrix. And the GRM also contains important information about sample composition, may it be the familial or cryptic relatedness, but also statistical power. And finally, linear models in general rely on likelihood for the estimation of parameters, which allows for unified testing, statistical testing of the parameters. So thank you very much for listening to this first part. I'm now going to talk a bit more about the genetic methods we use and where they fit in this statistical landscape. So thank you very much for your attention, and see you in part 2.